Hey guys, back with another DC-DC converter today, and looking at it, you can see that it's a buck converter. But you'd be thinking, why am I doing the buck converter again? I've already done it. So we're gonna be making a small change, and while that change is small component wise, looking at the schematic here, implementing it is not that simple. You have to change quite a bit of things. So that's what we're gonna be exploring today, and specifically this component. This is the freewheel diode which we put across, over here. So we're going to be changing that. So in a standard buck converter, you just have one PWM signal to control the high side MOSFET. And how it works is, standard. The more duty cycle you give, the more output voltage you give. So if you give say 0% duty cycle, you're gonna have 0 volts, because this is practically open circuited the entire time. So you're not gonna have any output voltage. And the higher duty cycle you give, let's say 50%, you're gonna have half. Ideally, you're gonna have half of the input voltage on the output. And if you give 100, you get your entire input voltage. But of course, that is in an ideal case. In reality, we have all the resistances, parasitics, so of course you can't get the entire output if you give 100. And we'll see that in the hardware. But nevertheless, the main thing what we're going to be changing today is, in the on state, the path is this way. It goes through the MOSFET, the LC, and yeah, it's a little bit to the output, the capacitor discharges, and towards this. And in the off state, we know the inductor, there will be a current flowing, and you can't just stop the inductor current flowing. So that's why you have this freewheel, that's why they call it. Then this will be the path through the freewheel diode, it will go through here. So one thing is, if you in low voltage applications and high current, both of them, low voltage, high current, the thing is that this diode, as we know, diodes, of course, they have a drop. And if you go standard silicone ones, then yeah, 0.7, 0.8 volts. And if you go for Schottky, maybe 0.3, 0.4, like that. But you can't quite go below 0.3. That's kind of the limit right now. So sometimes if you have, let's say, your output itself is something like 4 volts, and if you have loss, of course the diode is going to drop something. So you're not going to get 4 volts. You might get, if you even if you say you're using a Schottky, so it's not 0.7 but something like 0.3, you can't get exactly 4. So what they did is they replaced this diode with another MOSFET, and that is what is known as the synchronous buck converter. So they replaced the diode with another switch. As we know, diode is, of course, it's still a switch, but it's an uncontrolled switch. We don't have any control over it. Whereas the MOSFET, we do have control over it. So what we do is we replace the diode with another MOSFET, and we feed two PWM signals, one to this which was there earlier and another one here. And what we have done now is that, of course, we know today's MOSFETs, they have very low on state resistance, what they call RDS on. And the particular one which I'm using, which is a very standard MOSFET, the IRF Z44N, that has a on state of 17.5 milliohms, and that's very low. So if you have the same application, you have the 4 volts output, in this case the drop will definitely not be, I mean, of course, depending on your current, but of course it's going to be much lesser than that diode drop. So you're not going to drop, 0.3, 0.4 volts. So of course efficiency is going to increase. So that's exactly what this does. The synchronous buck converter, it's designed to increase the efficiency of the standard buck converter by replacing the diode with another MOSFET. So everything else remains same. The only thing is, now we have to generate two PWM signals. And if you see, this is the input voltage, right? If you just make, right now this is horizontal, if you just make this standing, this switch, you will immediately recognize that what we have here is a half bridge. And we know that in a half bridge, both the switches can never be on at the same time, because obviously if you have both on at the same time, it's directly going to get shorted, and you're going to have a big short circuit current flowing, and possibly blow up your MOSFET and all of that. So that is what we call a shoot through. It's called a shoot through condition. And of course, when this is on, this should be off, and when this is on, this should be off. That's how it was working in the normal buck converter, because the diode was reverse biased. So there you didn't have to do anything with it. But now, since you have put a MOSFET there, you have to handle that. It's a control device. So you have to give complementary PWM signals. So When this goes high, this goes low, complementary, a 180-degree phase shift, if you want to call it that. So complementary, but we know that in an ideal case, exact complementary signals would work, maybe even in a simulation. But of course, there are parasitics, and there are two main things which we need to consider. There are delays. All of these are not, ideal devices. So there is something known as, if you just go down in this data sheet here, somewhere it should be here, maybe lower. Yeah, here it is. So these things, just look at these four parameters. You have the turn on delay time, turn off delay time, you have the rise time, and you have the fall time. So these four parameters are important because they prove that it's not an ideal device. So I won't go into the signals theory of it, like what is rise time, fall time. Assuming that you know what it is, we need to account for these delays. So immediately when you give a signal, input signal, it's not, there is some latency in middle. So immediately it's not going to translate to the output. So you need to take care of that, and that's how you design what is known as dead time. So if you see, normally you would have, as I said, in ideal cases, you would have one PWM signal and just an inverted version of that. But here what we need is dead time, in which both the switches are off. So if you can see here, if this is our original PWM signal, which we're generating in the code, we're going to generate two different PWM signals, where one is our standard PWM and the other one, you can see this highlighted here, they have shown it nicely. This thing, if it was ideal, this would go lower at this point, but if you see, it's going lower before itself. So there's a preponed, this signal is preponed. So during this highlighted period, none of this is off anyways, and this is also off. So if you give enough dead time in between, you can prevent that shoot through from happening, and still drive the half bridge. So that's exactly what we're going to do. And on the other side too, that it's not a simple delay that it's only on the rising or it's on the falling edge, it has to be on both sides. So now you can see, ideally this would have gone off a little bit later, but you can see it's going off before itself, and again there's a dead time before this comes on. So this is exactly what dead time is, and we need to implement that in code. And in the earlier one, I have used the TL494 for the analog implementation, and the TL494 does have a push pull output mode, and it does have the dead time control pin, so you can do it in the analog way also. But that, it still has some temperature sway and all of that, and you can't have very precise dead time. So in code, I mean, it's these things run much faster, and after all, they are logic devices, so you can definitely, if you use a digital implementation, you're going to have more accuracy. So that's what we're going to do today. So we're going to generate the complementary PWM signals, feed it to the MOSFETs, and the power circuit remains the same. So just going into the schematic now, this schematic is similar to the buck boost converter, but you can see earlier there was only one optocoupler, and yeah, of course optocoupler is needed. Don't use microcontrollers without isolation to your power circuit. You have to keep that device protected. So we have two optocouplers here, the same 6N137, which I have used in the past, the high speed optocoupler, and the switching frequency, of course, whatever you decide, but I've gone for 50 kilohertz. So 50 kilohertz is pretty good, high. So I wouldn't say very high frequency, but it is relatively high, and your standard optocouplers can't handle that. They have very high, they have very high delays, rise and fall times. So this is a 10 Mbps, that's pretty fast, so this should do good. So we're going to use two of them, of course, since we have two PWM signals. We're going to generate them from code, get the isolation, galvanic isolation, and give it to the same IR2110 half bridge driver, which I'm gonna have used in the past. This time it's pretty common high side and low side driver. So that, and we have the bootstrap circuit for that. And finally, one more thing to mention, which I have, but I'll just mention it again. This optocoupler is a logic level optocoupler, so you can't directly give it 12 volts here. You have to give it up to 5 volts or maybe 3.3, but the 7805 is handy, so we'll just use the 7805 and get the 5 volt rail for the optocoupler. and the same to detect the signal, the IR2110 has to translate what is high, what is low. So you do need to give it here as well. And after that we have the isolated and power capable PWM signals, which can sync and source current, and that's what the driver is for. So you have the two complementary PWM signals with dead time, and now the diode is replaced with a MOSFET, and yeah, you feed it through 10 ohm. We do need something to reduce the ringing, so 10 ohm should be fine. You can maybe increase it depending on how your signal looks, but 10 ohm seems fine. And I'm using the same 12 volts, and yeah, the output, the L is 1 millihenry, inductor capacitor is 47 microfarad, and the load I'm taking is a resistive one, 47 ohm, so it should draw enough current. We don't want it to go into DCM, and I've designed it so that it remains in CCM. You use the buck converter formulas, those remain same, nothing changes. So yeah, the circuit is out of the way. Now we can go into the code, because that is another big part of this. The hardware is another, and the code also. So yeah, I'm going to be using the same MSP 430, which I have, I think, used in the past and made a video too. So it's a nice low power microcontroller from TI. So yeah, this is the code. And another one which I'm going to be using today, of course, this is still open loop, so we do need something to vary the duty. And yeah, we're going to be using the rotary encoder. So I have made a video on this too. It's just like a pot, you could say, but it has endless rotation. You can Pots do have limits, and they manually vary voltage. That's what a potentiometer is. But this doesn't really vary voltage. It sends pulses, and you can detect which direction it's moving in, and you realize it in your code. So it's much better than in a pot, in the sense that it's not really affected by temperature and other conditions, since it's not literally varying the voltage. You are seeing that it's varying the voltage. So yeah, the rotary encoder is there, so you need to implement the code for this too. So some of the code is reused from my older encoder video, that remains same. And yeah, we do need the lookup table for that, to assign how much one. All these encoders, they have tactile feedback, so if you do a small turn, you get that click. You can feel it in your hand, so you can translate how much you want one click or one pulse to be. So I have done around 2.5%. So each time you rotate it, around 2.5% of the duty, it will increase or decrease. So that is there. And yeah, some of the code is for the encoder. And yeah, the timer, this is one important thing. Since we do need the dead time, the if you use something like the STM microcontroller, STM32, that is famous too, that already has, most of those microcontrollers do have something known as the BDTR, the break and dead time register. And you can just enter the value. Again, there are formulas, but you just enter the value and it implements it all in hardware for you. But the MSP, at least this one, the 430 G2553, doesn't have that, so you have to implement it yourself. And you can still do it in hardware. We still use the hardware timer, we just change the modes up a bit. So standard, you for PWM you would use the up mode, but here we're going to be using the up down mode, because we want symmetrical PWM on both sides, and it's easy to do it. You can do it in up mode too, but up down mode, I just found this, and even the data sheet does mention it. So yeah, we use the up down mode. And we use the out mode 2 and 6, which is the set reset and reset set mode. And yeah, that is going to give us the complementary signals. And depending on what you give on these capture compare registers, and the period is decided by the CCR0 capture compare. So this is for 50 kilohertz. And for the dead time, this is all the rotary encoder code, so I won't really look into that. Let's just go into the uh, where is it, yeah, the dead time code. So it's just a small condition. We write the same value from the lookup table to both CCR1 and 2, but we just need to make sure one thing. If this value itself is less than the dead time required, then it will try and assign a negative value, and there's no negative integer. At least since it's if you explicitly declare it as unsigned, it's fine, but it may wrap around and give 65535. That's the 16-bit maximum value, and again, that would result in 100% duty, and if both are on, yeah, shoot through will happen. So we need to take care of that. So if it's negative, then we just assign 0. That's the lowest value possible. Otherwise you can, yeah, assign the dead same value as the CCR1 but minus the dead time. And the ticks part of it, I will leave it to you. It's not too tough to understand, but I can't go into the theory too much. It just defines how many clock, how many clock periods you need to keep it off. So yeah, those are the ticks. And now I think we have covered everything. The code is done, and we have the complementary signal, the driver, optocoupler, and yeah, dead time. So now we can go into the hardware. So yeah, coming into the hardware now, we have the oscilloscope ready. We can view the signals, and yeah, the microcontroller board, the rotary encoder, and yeah, everything on the breadboard. So as I said, two optocouplers there, they're ready. And we do need the pull-ups, of course. And this is the driver, the half bridge driver there. And after that, this is the power circuit. This is the one which you see on top here. I'll zoom out a bit. Yeah, the one which you see on top here, this one, that is the high side MOSFET, which is standard. And you can see there's no diode anymore. This is the low side MOSFET, which is going to be replacing our diode. And both of them, yeah, they need the 10 ohm gating resistor. It's a choke type or radial type inductor there. And yeah, we have the electrolytic capacitor, 47 microfarad. And as I said, we need 5 volts for the optocoupler. So yeah, a 7805, just run a perf board separately. And the load itself here, to, of course, these lids are a little big, so I can't really fit them on the breadboard. Ideally I should solder this, but yeah, nevertheless, I've just connected them using crocodile cables. So this is a ceramic or cement type resistor, 47 ohms, and it can dissipate 10 watts. So that's nice. It's a power resistor. We have the voltmeter here. You can see the output voltage, and yeah, one supply here to give the 12 volts. So yeah, that's the entire circuit. And yeah, a lot of probes and cables going everywhere. Just make sure nothing touches each other. So now we can power up the circuit and just flash the code once. So yeah, the code is flashed. And you might think, why is the LED glowing? But internally the pins which I'm using for the timer are also connected to the RGB LED. So yeah, you can ignore the light. But yeah, the circuit is powered up, the encoder is ready. And here we can see the signal. And of course there is quite a bit of ringing going on. If I just zoom in, and of course that's we're all doing it on a breadboard, so the inductance is probably acting up and the capacitance too. But nevertheless, you can maybe see that the dead time is implemented. I'll probably disconnect this power circuit later and just show you the PWM, so that you can see it without ringing. But currently you can see the yellow color one is for the top side switch, which is for the buck. And the blue color one is for the synchronous switch, which is replacing the diode. So currently we have only about 5% duty on the top side switch. So you can see the output is about 0.6 volts. So now I'm going to increase it a bit. And then or first, let's make it 0. So you can see 0% duty and on the top side switch. So we have practically 0 volts, which is completely off. So let's increase it a bit. And yeah, you can see the output voltage is increasing. So maybe let's go to something like 20%. So we go to 20% here. And yeah, we have about 2.4 volts. And yeah, 2.4. And you can see here the on timer has increased. And let's go to something about 50% duty cycle. So we have about 50% here. And now you can, I think, clearly see that this is going low earlier, as we talked in the image. This is going low earlier, and after some time, that is the dead time, this is going high. And same on this lower edge. And yeah, we have about 5.6 volts. So let's increase it a bit. And yeah, we are going towards 65% duty. And yeah, about 8 volts now at 73% duty. So let's maybe take it to, uh, 85, 90, and maybe we can go up to 95. Of course you can go up to 100 itself. That is just going to give you your input voltage, but yeah, now you can see this thing is practically zero, because do know that the lookup table which we have made, if you give too much dead time, there is some problem too, because you're going to lose resolution of the PWM. So make sure not to give too much dead time, but don't give too low too. If you give it too low, I mean, again, shoot through might happen. So it's a trade off. You need to decide by yourself. But yeah, you can clearly see that the bucking is happening and the synchronous switch is working properly. And yeah, that was the whole point. I'm just decreasing the duty cycle now, can bring it back to 0. So yeah, you can see 2.5% duty decreases, and this is up to you. You can even give 1%, or you can give 10%, and that's the beauty of using an encoder. You decide how much duty cycle you want to reduce or increase. So yeah, back to 0, and yeah, we have 0 volts. So yeah, this was, just switch this off. So yeah, this was the whole point of the synchronous buck converter here. And the learnings out of this is, of course, the half bridge needs dead time. That's a term that gets thrown around a lot in power electronics, especially any kind of power converter which uses a half bridge or full bridge. So this uses a half bridge, and later if you might want to drive a motor or something from this, you can do that too. It's a buck converter. Here I used a resistive load, but yeah, you can go for a motor too. And see the motor speeding up and slowing down. And another thing is, of course, digital is good. I Any error is there, you can always just debug it in if you try to do it in analog, that's good too, but you would have to mess around with some RC values to adjust all of that. But yeah, the MSP is good, and the power electronic circuit worked out fine. And if you maybe lay out this properly, maybe this driver on a puff board or maybe on a PCB, we can maybe reduce these parasitics, how much it's affecting. And of course these breadboards do have the inductance and all of that, but just as a POC it's good enough that we can see the bucking action happening. So yeah, that was the whole point of today's video. So I hope you liked it and learned a thing or two. So yeah, thank you.